How you doing? Today, we'd like to talk about the next unit, right? Unit 4, right after the simplex method. We're kind of switching tracks a little bit, right? Today, and in Unit 4, we're going to be talking about probability and statistics a little bit, but mostly probability. It does feel like a quantum leap from where we just came from. It kind of is. Right? We're basically starting a brand new math class because a lot of these topics are covered in Math 1342, which is introductory statistics. But that's okay. We're just going to grab some of the important concepts out of that class to finish out the semester, and that will be just enough, right? I'm going to try to trim it down to just the bare minimum that we need to get by in this class. Before we start talking about probability, though, I do need to mention about sets, because sets are sort of the language that we use to discuss probability. So I can't really discuss probability without having a base knowledge of sets first. Sets is one of those definitions in mathematics that is almost circular, because we designed sets to be the most generic collection of things, right, possible. Right? The idea of sets should be able to take us anywhere. Right? So if something is true for all sets, it is true for any collection of anything. Right? It doesn't depend on what is in that collection. Right? It's just the most primordial rule about collections of things. And so I've got the definition here on the tablet. Right? A set is a collection of elements, and an element is a member of a set. And that, if that's delightfully circular, then it's kind of supposed to be a little bit, in the sense that we don't want the sets to be the thing that we are studying. This is not a set theory class. We just want the sets to stand in as sort of a generic collection of things. And this is the most generic definition we can give. Most of the times, the types of sets we'll be looking at are numbers, or maybe we have letters, or again, we want it to be super generic. The notation that we use for sets varies depending on what kind of thing is in the set, but most of the time when we're talking about sets, and in the sense that we can make a list of all of the things in that set, the notation will look just like it does here at the bottom of my screen. We'll use these curly brackets, and I know that they're never fun to draw. So we'll use the curly brackets to mean here are the things in the set. You might call this the roster method. We'll make a full list of all the things which are in the set. They don't have to be in order, although it's kind to put them in order, especially if you want your reader to be able to find whether or not something is in there or not at a glance. It's kind to put them in order, but not everything which goes in the set can be put in order. Right? How do you put things like different colors in order, right? Maybe a color theorist would have some way to say, okay, well, maybe we'll organize them by hue angle or something like that, but not everything can be put in order. I know that's kind of a weird concept, but so we'll do our best. I will do my best to not deceive you in my lists of sets. We'll also have things like set builder method. We won't see that quite as often in this class. It looks like the roster method, but instead of telling you what the members of the set are, I basically give you the definition. And I'll say, okay, well, this set contains all values x where or such that x is between 0 and 20, for example. So that's called set builder notation. We don't see that one quite as much in this class, but that's okay. Right? Just in case it comes up, or just in case you see it in a textbook or somebody else uses that notation, I just want you to know what it is. Basically, it's a way to say, well, I'm not going to tell you everything which is in the set because there may be a whole bunch of things, but I will tell you how to build that set yourself. You could figure that out. Is that a member of the set or not? I've given 3 example sets here. Like I said, they don't have to be in order, but it's kind to put them in order. Sometimes we'll also see sets which have a pattern to them. That is, if I wanted all of the numbers between 1 and 10,000, for example, that would be a very burdensome set to write down in the roster method. Right? A set builder notation might be okay because I could change that 0 less than x less than 20 to a 10,000 or something like that. Not so bad. But I could still kind of do it in the roster method this way. I would say I would give you enough numbers, usually 2 or 3, to establish what the pattern is, and then ... ellipses says you fill in that pattern and you stop at the number 10,000. Not too bad. Other sets may go on forever, literally, right? They may have an infinite number of elements within them. And so those dots may appear at the end of the list with nothing after it. And that would indicate that set goes forever. Again, we don't get into sort of the philosophy behind infinitely many things in a set too much in this class. Although it's not hard to imagine, right? It's just like a number line, except I don't have any decimal values in between. We don't see it too much, right? We're going to try to stick to small sets when possible. But that is our set notation, and we use the little curly brackets. Set, you've probably noticed set names, right? The name of a set is usually a capital letter. I'll try to stick to that pretty hard in this class, right? And the name of a set must be a capital letter. So let's look at some of the ways these sets can start combining together. And we don't have to go too far into, like I said, the set theory aspect, but we do need to know how to combine these sets. Otherwise, it's just, hey, look at this set. Isn't it great? Look at this other set. Isn't that great? Nothing happens. Right? Using the set notation with all the operations allows me to start combining these sets together and get more useful results out of them. So the first note, you probably already are familiar with some of these. You may have seen them in a previous class. The first one is in the union notation. I know that symbol between the A and the B looks like a letter U. It's not quite. You notice how it's a little bit smaller. It's set up off the baseline. It's not on the baseline, right? The letters sit on the baseline. They can go above or below like a Y, but the U is sort of set up off of it, and there's not a tail on it. When I write a letter U, I try my best to put a tail on the U, right, to distinguish it from this symbol, which looks very much like a U. As a matter of fact, in my open math, to type this into the box, you can either click the button or you could type the letter U, right? So it looks so much like the letter U that it's might as well just call it the letter U, and many people do. So in this union, I want to put two sets together. A union B is basically a new set which contains all of the elements of set A as well as all of the elements in set B. And so if I wrote that in set builder notation, I might write it like this. And so I want all of the elements X such that X is a member of A, and that's what this symbol, I know that symbol looks kind of like an E. Right? This symbol means is a member of. I'm going to have to erase this, but I wanted to write it big so you could see what that symbol is supposed to look like. And again, it's supposed to be set up off the baseline a little. I'll go back and I'll add this to the notes after class. I'll find a place to tuck it in here. But that's what that notation means if you see me or someone else use it. This is a member of A, or X is a member of set B. And the word or in there I've capitalized because I'm using it in sort of the strict logical sense. If you've ever taken philosophy class called logic, you would have studied the rules of logic. And this or is a logical or. For the most part, it matches our intuitive understanding of what the word or means. Although we have to be careful because in English, when we say the word or, we're usually talking about either or, right? But not both. You've probably heard plenty of jokes like that. Would you like French fries or would you like ice cream? Yes. Right? The joke is that yes, I want both. Right? The word or in the logical sense contains the possibility of both. Right? But in English, usually when we say or, we mean either or. Right? We mean would you like French fries or would you like ice cream implies that you can't have both. So in the logical sense, it does include both, which is why I use capital letters to show the logical word or. I'm going to do the same thing for the logical word and in the next definition. So the logical word or. If I were to make a Venn diagram, like you see a couple of my Venn diagrams listed here, this is how we'll usually see sets in a Venn diagram. It's very sort of generic shape. Things that are inside of the circle are inside of set A. Things which are outside of the circle labeled B are outside of set B. And if I were to highlight, A union B would be this region which is in A or in B or in both. This is A union B. Notice how it's the A part, the B part, and the part in between, which is both at the same time. That's, again, it's something we'll have to correct for later on when we start dealing with formulas and we're counting. That's the reason why I'm emphasizing this. The union includes both, because basically I don't want to double count the things which are in set A and in set B. Right? If I said I have 5 things in set A and 5 things in set B, how many are in the union? Right? Naively, you might say, well, there's 10. There's 5 in A, there's 5 in B. But if there's any overlap, that might not be true. So if my Venn diagram looked like this, there's 5 things in set A and 5 things in set B. It just so happens that, or excuse me, like this, there's complete overlap between them. Everything in A is in between, right? It's both in set A and B. Everything in set B is also in set A. So there are 5 things in A, there are 5 things in B, but there are only 5 things in A union B. That's kind of the most extreme case. We don't usually see cases where everything is in that overlap, but that is the most extreme case. Normally we would have something like this, maybe 1, 3, that would be 2 and 3. I want to make sure that there's 5 in the set, and 2 like that. So you might say, well, there are 5 things in set A, because everything inside of the A circle, there are 5 total. There are 5 things in set B, everything inside of the B circle, there are 5 total. But how many are in A union B? That's the entire thing. Well, that's 3, 4, 5, 6, 7. There's 7, not 10. And the reason for that is because we don't want to double count those 3 in the middle. Take a look for that when you're looking at your rules this week. Again, that's why I had to emphasize so much the both part of this union. The intersection rule, if I want to combine 2 sets and look at their intersection, I use basically the upside down version of the previous symbol. It looks kind of like a lowercase n, but again, it's one of those up off the baseline. It's centered on the line, kind of like a plus sign. You know, like a plus sign sits in the middle. Same thing for this intersection symbol. In set builder notation, it would look like this. All the elements x, such that x is a member of set A, so it's in the A circle, and, logical and, x is also a member of set B. So it's in both. If I were to draw that as a Venn diagram, that's just this region here in the middle, and the intersection region, in both at the same time. Complement, a little bit weirder. complement is usually either notated like this with a big C, or some books will notate it like this with a prime symbol. It's just kind of like a little tick mark. A tick mark, a complement. Okay? And so the a complement, the idea there is we want to refer to the things which are not in set A. That looks like this. All of the elements such that this X is not in set A. Okay, the slash works for this symbol much the same as it works for an equal sign. Slash equal sign means not equal to. So slash, the sideways E looking symbol, right, the membership symbol. And so X is not a member of set A. We have to be careful here, because when it comes to sets, remember, anything can be a member of a set. And so if I say, well, what is not in this set? Well, maybe a soda is not in that set. Maybe, right, a Ferrari is not in that set. Maybe the color green is not in that set. And so it's not super useful to talk about not being in a set unless I have a limit of, well, what are we actually talking about here? Right? I want to know, constrain the conversation of what we're talking about before I introduce this idea of not in a set. And that's what that rectangle box around most Venn diagrams are, right? Especially ones in this class. Sometimes this set is called the universe set. And sometimes it's given a letter U. I don't like using the letter U, although a lot of textbooks and a lot of homework problems will give it the letter U, just because it looks too much like the union symbol. I will usually call it S because I'm kind of using a probability term from later. We'll call that the sample space later. So I'm usually one to call this set S instead of U. But either way you're looking at it, I'm going to amend my definition for complement to say, well, X is not a member of A, but X is a member of sample space or the universe set, depending on which notation that you're using. So the universe set or the sample space give me some way to limit what we're talking about. Right? If we're trying to have a conversation about numbers here, I would rather not talk about forks and spoons. Right? That's not part of this conversation. And the universe set is a way to say, well, my conversation only is referring to these things. If I were to draw a Venn diagram for this complement, then it would be everything outside of A. Notice how the definition for this complement doesn't refer to B at all. I didn't even need B to be in this picture. I just copied this picture from up above where B was already drawn into it. You see how it's everything outside the circle, outside of set A. And if you've ever dealt with logic words before, then these three definitions capture the basics of logic: and, or, not. Right? If you're a computer scientist or if you've done programming before, right, and, or, and not, right, will allow you to do pretty much everything with it. Right? That is the basis of logic: and, or, and not. Just be careful that you're using the logical word or and the logical word and when you're reading the questions in this class. Let's do some examples. I didn't have room for examples on this screen full, so I've got them a few examples written down below. I just wanted to give you a chance to get these in your notes or get these all seen at the same time so that you can refer back to it in this screen if you need to. Okay, so I've got a couple of sets here. These are the same A, B, and C set from up above, right at the very beginning. But now I've added a universe set U. Here I am using that U symbol. Notice I always put the tail on it. Let's look at something. Let's see. If I wanted to talk about A union C, remember that is everything that's in set A and everything that's in set C. And you have to be careful. Notice how I said and, but up above wasn't that supposed to be logical or? Yeah, right. Again, our intuitive English, right, phrasing of and, I want this stuff and this stuff, doesn't match the logical and or. We have to be careful there. I'm going to write down all the members of set A. I'm going to use the dots, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And also I'm going to include everything in set C. You might be scratching your head a little bit. One, because these are not in order. Right? We said it doesn't have to be in order, it's just kind. And two, because some of these things are duplicated. Generally, we do not duplicate members of a set. It doesn't mean anything to be a member of a set twice. You're either in the set or you're not in the set. So when I rewrite this, because 5 and 10 appear in the list already, I'm not going to bother to write them again. So while it would not be incorrect to write it the first way, I would not choose to do so. Because I want to make sure that if possible, I can put these in order. I want to make sure that if possible, I'm not duplicating any members of the set. And that's just kinder to your reader. And notice how this particular set is kind of a combination of the dots to show a pattern. And once that pattern is over, there's some more. So we have to be a little bit flexible when we see these notations. So A union C, this set here, the numbers 1 or 0, then 1 through 10, comma 15 and 20 as well. You might say that the number of things which is in this set, I might have to count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 0, 15, and 20. There are 13 numbers in this set. So sometimes your textbook might show that as N, A union C is 13. And that N, right, that's really a function kind of thing from college algebra, but we don't require college algebra to be in this class. So I'm going to try to stick to not function notation for as long as I can. Some other textbooks might write this as, it looks like absolute value symbols. Get the straight up and down line, called the cardinality. So sometimes you'll hear that referred to as the cardinality. And again, for this class, that's just the number of things within that set. We don't want to bring up all the craziness which comes with discussing the actual idea of cardinality. Let's look at some other examples here. What if I wanted to do a intersection C? A intersection C are only those things which are in common. So which are the numbers which both have in common? I see 0, both of them have 0. I see 5, both of them have the number 5. 0, 5. Both of them have the number 10. 10. And I think that's it. So this set, only the overlap and the cardinality of this set is 3. Or 3 members of this set. Okay, not too bad. About this one. A complement. And in this case, notice how when you're talking about a complement, I do not have to list for you what the universe set is. I don't do a complement with respect to the universe set U. That's kind of implied. I don't have a good way to show you in this class, well, this is what the universe set is, and I want A in that universe set. Some textbooks would show it like this. They might say, take the universe set and subtract from that universe set the set A. Right? It's an acceptable notation, maybe in a different class. We don't see this notation that much in this class. Universe set slash means take away from that universe set A. Most often in your textbook, you will see this complement notation. Things which are not in set A, but are still in the universe set. So let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all in the universe set. But these, 11, 12, all the way to 20, are not in set A, but they are in the universe set. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 10 elements in that set. So the cardinality of that set is 10. So these operations can stack up. Right? I've been doing them one at a time, but it's certainly possible to stack them up. So yeah, if I wanted to do A intersection B union C, all of that complement. Oh my goodness gracious. It's actually several sort of operations, right? We're not going to cover what the quote unquote order of operations is for these things. If I ever ask you to do multiple operations, I will make it clear by the way that I put parentheses which order those operations should be conducted in. For example, if I didn't have these set of parentheses, if we went over the order of operations, then you would have to know that it has to occur first, kind of like multiplication comes before addition in the order of operation. But again, that's not part of this class. So let's do it in this order. So A intersection B, we haven't talked about that one before, so let me put that here. So A intersection B, looks like that is 1 through 10. Okay. So after we have A intersection B, I'm going to union that set with set C. And 1 through 10. Oh, but wait, C has 0 in it. I'm not going to list 5 again because it's already there. I'm not going to list 10 because it's already there. But I will list 15 and 20. Again, I know those things are out of order. Right? I will be kind in my final answer and write them in order. But I'm still working here. Okay, now I want all of this complement. This is everything which is in the universe set which is not already listed. So I've already listed 0, 1 through 10. Looks like I just need 11, 12, 13, 14. Not 15. 16, 17, 18, 19. Not 20. It's already listed. Oh my. Right, so again, there's 3 operations in a row there. So all of that is a single set. Kind of like when you add 2 numbers together, you get another number. Well, when you do these operations to a set, you get another set in return. So I can talk about the cardinality of this nasty nonsense here. That would just be me counting. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 members in that set. I know it looks a little bit complicated at first because of the notation, right? Give yourself a little bit of slack when it comes to the notation, right? And practice the intuitive, well, what's going on here? You'll find that it comes a little bit easier if you kind of go with the flow with, okay, well, what is this? I'm talking about sets here. I'm talking about notations. What's in this set? What's not in this? It will come with practice, I promise. None of this stuff comes 100% naturally, but it does come with practice. The reason that we talked about sets was because sets were the language of probability for us. So here's why we really talked about sets, because we want to use sets when we're talking about probability. Probability is a new study for us. It's something which is brand new, right? And it's really outside the realm of normal mathematics. If you were to go on to study mathematics at a university, probability is its own department outside of the math department. And so, yes, we use a lot of math notation and numbers and very similar tools as math, but probability is actually a separate study than math. Probability is the study of uncertainty, right? If you think about everything in math was certain. There was no guesswork in the sense that everything worked one way and only one way. I just had to find the right definition and do the right process. The answer was always the same. No guesswork, no possibilities, no probability. But in probability, right, we would like to study, well, what happens if that's not true? What if we are uncertain as to what will happen? Later on, we'll talk up and give these things more formal names. But what if I have a coin flip? I flip that coin. Sometimes it comes out heads. Sometimes it comes out tails. And maybe that's what I want to build my universe set from. I want to say, well, it could be heads or it could be tails. I do not know which one. I want to exclude from that universe set where it lands on its side, right? It doesn't happen often enough that I'd like to consider it. I'd also like to exclude from my universe set the possibility that the entire world ends before the coin comes back down. Right? You see that the universe set is a very useful way for us to eliminate all the possibilities which are not what we're trying to study. So I could build a universe set out of all of the possibilities, which for a coin will only be heads and tails. Like I said, we use probability as a mathematical feeling tool, but it is a brand new set of tools. So I need to give the definition of a probability assignment. Right? Sometimes the textbook would call this a probability assignment. And it has to follow a few rules. So that probability assignment must be between 0 and 1, right? Every element of that probability assignment must be positive, and actually, it must be between 0 and 1. And it's including 0 and 1. You can think of 0 and 1 as sort of the very extreme points of probability. 0 is the extreme on one side, 1 is the extreme on the other side. It must be between 0 and 1. And the probability of the universe set must be 1. In that sense, right, basically the probability of the universe set says the probability that something in this set happens is 1. And if we're defining 1 to be the extreme most probable thing to happen, and we're defining the universe set to say, well, this set contains everything which could happen, then by definition almost, we want to make sure that this universe set has a probability of 1. If it's not 1, then you either misdefined your universe set or you've miscalculated your probability. By definition, we want the probability of that universe set or something within it, right, to be 1. And then for 3, these probabilities must be additive in the sense that if I want two things to be the probability of those two things, I want them to be able to add together. So if I have this union set here, if set C is the union of A and B, the probability of that set C is equal to the probability of A plus the probability of B. And again, I'm going to try not to use too much of this function notation, but I needed some way to show you that the probability of set C, the probability of set A plus the probability of set B. And the shortest way to do that was with that functiony notation. You won't be able to check number 3 most of the time. I think the homework asks you, it kind of does. I think the homework will give you some problems where it gives you a list of all the probabilities, and you can check that when you add them all together, do you get 1? And so I guess it can check to see all of 3 of these things at the same time. Okay, so in this class, there's lots of different ways to interpret probability. If we were in a statistics and probability class, we would probably have to go over several ways to interpret probability. It almost feels philosophical because it kind of is. Because again, humans have invented probability, so we have invented how we're looking at this probability. For this class, we're going to try to keep it simple. We're going to count up the number of things which are possible. We're going to say, well, how many of those things, right, are we talking about? And we'll just divide to get that probability. And it's called the frequentist approach. If there are 10 possible events, right, and what I'm looking at is 4 of those events, then the probability of that happening is 4 over 10. Out of the 10 things which could happen, 4 of them are what I'm studying, 4 out of 10. Right? There's some assumptions there, right? There's that assumption that every one of those things is equally likely, which may not be true. Right? Maybe it is true if we're rolling a dice or flipping a coin or drawing something out of a deck of cards. Maybe assuming these things are equally likely is okay. But in the real world, maybe not. Maybe that's not okay. Later on, we'll have to talk about some tools that we have. How do we address this when they're not equally likely? But for this first chapter, everything should be equally likely. We're spinning spinners and flipping coins and picking balls out of boxes. All those sort of things are very easy to make that equally likely assumption. I'll even write that here. Sometimes this is called the equally likely assumption. And it is an assumption. Just so you know, right? We will assume. Okay? So, like maybe you'll have word problems in your homework that talk about the probability of having children, boys and girls. They'll assume that it's exactly half and half. Although if you were to go and conduct a medical study, you might find that it's not exactly half and half. I don't think it actually is. But I'm not a medical doctor, so don't take my medical advice. We are making an assumption. Just an example of that assumption. Let's say that we're rolling a 6-sided die. 1, 2, 3, 4, 5, 6. So in that case, the number of possible things which could happen is 6. And if I wanted to write the sample space or the universe set, I'll write it with an S. I could say the number of things which could happen, and it's somewhere in here. Again, I'm excluding the really weird possibilities that dice falls off the table, including the possibility that it explodes or it comes to rest. Those are not useful to study. So let's see. If I wanted the probability of rolling an even number, so let's count all the ways that I could roll an even number. That could be a 2, a 4, or a 6. And so I will say the probability of that happening is 3 things, because I've counted 3 things, 2, 4, and 6. 6. And I'll reduce that fraction to 1/2. There you go. So if it seems easy, it's because it is easy. I'm not going to try to stump you or pull trick questions on you as in the homework. Some of the questions will require some careful thought, but most of them are pretty straightforward when you break them down. You have your list, you're just counting things from that list. See, what if I want the probability of rolling not a 1? And that's that not that's happening, right? That complement idea. Rather than worry too much about the complement idea, right? I don't want to write the list of things which is in that complement. Let me just count all the things which are not a 1. 1, 2, 3, 4, 5 things which are not a 1 out of 6 total. 5/6. You could express that as a decimal, but I guarantee you that decimals are going to be harder to work with probability. I know no one likes fractions. If you don't like fractions, that's perfectly fine. Get yourself a calculator which can work with fractions. My calculator is a Casio 115 ES Plus. You can get one for less than $20. Even better, you could use an online calculator which does fractions and doesn't cost you a single thing. Right? I think I've linked to the Desmos scientific calculator from my Open Math. Feel free to use that calculator as you're working on your questions, as you're doing your test. Just make sure that you need to show me the steps, not necessarily the calculation. You can show me the steps, what you're thinking, without showing me all the calculation. All right. I think that's the basics for this week. There are a few other things which you'll need to refer to the notes and the other links to, but I think we've got our basics covered this week. I will see you later. Have a good one.